Two-dimensional motion. In this lesson, we'll be covering uniform versus non-uniform motion, vectors, x and y vector components, vector component addition, and then we're going to do some practice. Uniform versus non-uniform motion. Uniform motion is a movement at a constant speed in a straight line. Non-uniform motion means a movement with changes in speed or direction or both. So uniform motion would be constant speed, straight line. So if we had something like 5 meters per second east, that would be uniform motion. Non-uniform motion would be if we have a different, so either we can have two different versions. We can have a straight line, but with a varying speed. So if this is 5 meters per second, and then we go up to say 8 meters per second, both are going to be in east direction, that's going to be non-uniform motion. But we could also have a constant speed, but a changing direction. So if we have 5 meters per second, that stays constant, but of course our direction is going to change, then that's also going to be non-uniform motion. Vectors. Vectors involve a magnitude and a direction. So it's different from scalar quantities, which are simply magnitude. Vectors are going to also have that direction component, so the east component, for instance. So for example, 100 kilometers per hour east would be drawn as a horizontal line with an arrow pointing in the intended direction. And usually what we do is we draw a compass in the top or some kind of directional coordinate system to indicate which way we're moving. Sometimes it might be something like this that says forward. That's also fine. So we're going to have some kind of directional components so that we know which way is which. And in this case, since we're going east and we have our compass at the top, our 100 kilometers per hour east would be drawn with this arrow going to the right, and we'd have 100 kilometers per hour. And we could identify east again from the compass that we drew in the top right-hand corner of our screen. However, most of our movement occurs at some combination of the horizontal and vertical, so some kind of diagonal movement on this coordinate system. So for example, 100 kilometers per hour east, 50 degrees south would be drawn with an arrow pointed east, but directed 50 degrees southward. Now you might also see this as written as 100 kilometers per hour, 50 degrees south of east. And you got to keep in mind that that is the same thing as east 50 degrees south. Vectors. When you look at a vector, you can break it into its horizontal, its x, and its vertical components. So if we have our diagonal vector here on the left-hand side in black, you can see that we can break that down into our red vertical and our blue horizontal. And we can do this with any kind of direction. We're simply going to take the vector and break it into its components. So how do we break our vectors down? Well, we're always going to assign a positive direction. That's going to be very, very important. I talked about the compass before. Typically what we can do is we can simply draw this compass in the top right-hand corner, as you can see right here, indicating which way is positive. So in our case, if we were saying north was up and east was right, we could include those parts on this coordinate system as well. So we've assigned our positive direction. We've said up and right, or in this case, north and east are positive. And we got to keep in mind that each component of our main vector will be less than the main component. So our components are always going to represent part of the entire whole, but not equal parts. So for instance, if we had a line that was 100, it's not like this needs to be 50 and 50 or 30 and 70. It doesn't break it down like that. It just means that if this guy is going to the right, it's going to be a portion of that 250, and we're going to see what that is in a second. So we're going to have to use our knowledge of trigonometry to solve for the x and y components of these different vectors. So let's break it down here. I'm going to use two different colors. I'm going to have red for my vertical, and I have blue for my horizontal. Now to find the red, if we use trig, this is the opposite side, so we can use sine. So we can say sine of 30 equals, that's opposite, over hypotenuse, which is 250. Now if we were to rearrange that, it would also be opposite. I'm just going to do that to make it seem a little different, to differentiate it from our zeros. Opposite is going to equal to sine 30 times 250. And usually how I write it is 250 times sine 30. I find it makes the most sense, and it's easier to write and differentiate one side from the other. So 250 times sine 30 equals 125. Now we can do the same thing for the adjacent side. So the adjacent side, that's going to be our cos. So now we're going to say cos 30 is going to be adjacent over 250. We can rearrange just like we did before. So we're going to put the 250 up front. Cos 30 equals A. So adjacent side is going to equal to 216.5. And now we've broken into our components. And you can see what I was saying earlier. This 250 isn't broken into even like 125, 125, or 250. This is 216 and 125, but you can see that they're both less than 250, and that's going to be the key. If you get a number, a component of our vector that's greater than the actual vector itself, you know you made a mistake somewhere. And this slide is just showing the exact same thing. So you can see how we solved. We solved for the y component here, we solved for the x component here, but we followed the same steps that I just did on the previous slide. Now the last thing is that you can see that they're both in the positive direction. We went to the right and we went up, which is what our coordinate system said were positives. Now, there's no set right is positive, up is positive. It could be left is positive and down is positive, in which case we would have had negative numbers for both of these, but we'll get to that in a second. So now similarly, we can break down this vector into its components as well. So let's draw our vectors again, and let's break them down. Let's do the y first. So the y, that's going to be the opposite angle, the opposite side, demonstrate that part out, the opposite side to the angle, right? That's the opposite side. So again, we're going to use sine 35 equals opposite over the hypotenuse, which is 2.1. Now we're going to rearrange. We're going to solve for the opposite side, which is going to be 2.1 times sine 35, which equals to 1.20. Now our hypotenuse, our vector, is in kilometers, so kilometers. Now the x side, in this case the adjacent side, and it's not always going to be that way. The adjacent side is going to be cos 35 is going to equal to adjacent over hypotenuse, which is 2.1. We can rearrange. We can say a is going to equal to 2.1 cos 35, and that equals to 1.72 kilometers. Now we need to do something. We should have done this at the very beginning. We need to have a coordinate system, a positive direction. Now I said up and right were positive before, but since our vector is obviously going right and down, we can more easily write this one as right and down as positive. Again, it doesn't matter what direction you pick, as long as you pick a direction. So that gives us our x and y components are both positive numbers, which makes our math a little bit easier. Now further on, we have 2 sig digs in our question, pretty much everywhere. Our degrees are 2 sig digs, our number here is 2 sig digs, so our answer should have 2 sig digs as well. So let's finish these off here. 1.7 kilometers. And we're done. We got our vector components. Now similarly, let's do it again. So I'm going to draw my vector here, my x here. Again, the y value is going to be opposite. So I'm going to say, let's do the right color, opposite, and then we have adjacent. So let's do the y first. Now before we go anywhere, let's pick our positives. We're going right and up, so let's just say that right and up are positive, in this case east and north. So in our y, it's going to be sine 60 is equal to opposite over 50. We rearrange, we're going to say opposite is going to equal to 50 sine 60, which equals to 43.3 meters per second. Now our x, similar, that's going to be our adjacent side. So we're going to say cos 60 is going to equal to adjacent over 50. We're going to say a is going to equal to 50 times cos 60, which equals to 25 meters per second. And again, you can see that it's a component of this 50. It's a part of the 50. Both of them are less than 50, but again, they don't add to 50. Now at this point, you should see a little bit of a pattern in terms of how we're going to set this up to make things a little bit faster. And we'll do that on the next slide. But you don't need to go through this whole process of sine 60 equals opposite over 50, for instance, for the y. You can simply see, okay, well, it's opposite, so it's going to be sine. Right? Anytime it's going to be opposite, that's going to equal sine. It's going to be the angle that we're given, right? We're told. Now we're going to put this number first. So right away, you should be able to see, okay, for opposite, it's going to be 50 sine 60. And that's going to make your math a lot easier to do. Vector component addition. So for more complex problems, we need to do a couple more things. First of all, we're going to line up each vector head to tail, like we have shown in this picture right here on the right-hand side. We're going to break down every vector into its x and y components like we were doing previously. And we're going to determine the sum of the x and the y components. We're going to find out the x's individually, and then we're going to add them all together. We're going to create a right triangle with our x and y components, and then we're going to solve for the hypotenuse and angle using trigonometry. Check your understanding. Now we can bring everything together. Let's first draw our positive directions. We're going to say right and up are positive. After leaving the huddle, a receiver on a football team runs 8.5 meters east, waiting for the ball to be snapped. So we're going to go 8.5 meters to the east. 8.5. Then he turns abruptly and runs 12 meters south. So this vector should be a little bit longer. 12 meters south. Suddenly changes direction, catches the passes, and runs 13.5 meters west before being tackled. So again, this vector is a little bit longer. And we're going to say 13 meters. The entire motion takes 7 seconds. So time equals 7 seconds. Change colors up here. So what is the average speed? Well, speed is simply distance over time. Distance is going to be 8.5 plus 12 plus 13.5 divided by 7. And that's going to equal to 4.86 meters per second. No direction because speed is simply a scalar quantity. Now, how many sig digs do we need? Well, we need 2 sig digs, right? We have 2 there, 2 there. So your final answer for A should be 4.9 meters per second. Now, B says, what is the average velocity? Now, to find average velocity, that's a little bit more complicated. Velocity is going to take into account displacement over time. So we got to figure out what the displacement is. So we know it's going to be something over 7. So now we got to break it into its components. So let's use the y component first. The y component is going to include everything that's going in the y direction. Now for us, that's only this component here, but we're going to go to each 3 just to break it down even more. So the first one, that's 0, because it doesn't go in the y, it only goes in the x. Now we're going to add. Now we're going down. We said up was positive, so we're going to add negative 12. And then we're going to go left, so again, that's another 0. So we come out to negative 12. For our x components, we're going to go to the right, so that's plus 8.5. We're going to go down, so that's 0. And then we're going left, so we're going to add negative 13.5 meters. I wrote 13, but that's 13.5. 13.5 meters. And when you add those up, you get negative 5. So now on the instructions, it said now we need to draw our triangle. Now it doesn't matter which way you go first. It doesn't matter if you go the x component or the y component first. Now they're both negative, so they're going to go opposite to what our initial coordinate system was. So we're going to go left and we're going to go down. So let's go left first. So we're going to go left 5. And we're going to go down 12. And then we're going to draw our hypotenuse. And the hypotenuse is actually going to be the displacement. So how do we figure out the displacement? Well, that's just Pythagorean theorem. So in this case, it's going to be the square root of 5 squared plus 12 squared. And that equals to 13. So that's 13 meters. And that's our displacement. Now the last thing we've got to figure out is this angle right here. Now to find theta, theta is going to be equal to tan minus 1, opposite, which is 12, divided by adjacent, which is 5. And that equals to 67 degrees. Now, why is it tan inverse? Well, we're looking for the angle, so it's always going to be the inverse. We have opposite and adjacent. You can also use hypotenuse, but I typically just stick to tan, negative 1. Inverse tan is just something constant, easy to remember. You don't have to change things up. It's always going to be inverse tan of the opposite over the adjacent. So let's leave it at that. So 67 degrees. So now we have our displacement is actually going to be 13 meters. Now we're going, in this case, west, 67 degrees south, because we went west and then south. So now we have all the information. So going back up to our equation here, v equals d over t, we know that d is 13. So our velocity becomes 1.9 meters per second, west, 67 degrees south. And that's our final answer. Check your understanding. In 4.4 seconds, a bird flies in a horizontal plane from post P to a house H and then to a bird feeder F, as shown below. Find the following. Total distance traveled. Well, that's simply going to be 22 meters plus 11 meters, which is going to equal to 33 meters. The average speed is going to equal to distance divided by time. So 33 divided by 4.4 seconds gives us 7.5 meters per second. Now C, total displacement, that's when it gets a little bit more complicated. So now we need to break it into our components. So our components, we can draw them in from our diagram we already have. But first, let's draw in our positive direction. So let's just say that right and up are positive. Again, it doesn't matter what you pick, as long as you pick something. So right and up are positive. So now when we draw our coordinates in, we're going to draw our x coordinates first. We have that, and we have that. And then we're going to go up, and we're going to go down. So let's start with our y components first. So our y components is going to be this first vector that we have right here. Now, we talked about the shortcut on the previous page, and that's what we're going to follow in this one. So instead of going through all the steps, we're just going to take the vector, which is 22, its opposite. So we say sine 33 is our angle, and it's going up, so we know it's positive. Then we're going to add. Now, in this case, it's going to be negative, so I'm going to put brackets around it because it's going down. We're going to say 11. It's opposite again, so we say sine 28, and that's negative because it's going down. So when you add these up, you get 6.82 meters. Now we need 2 sig digs in our answer, so we're going to keep 3 throughout. You always keep 1 extra. So let's take a look at the x. So the x are both going right, so we know they're both going to be positive. So we're going to have 22. This is the adjacent side, so it's cos 33 plus 11 cos 28. And that gives us 28.2 meters. So now we can set up our triangle. They're both positive, so we know we're going to go right and up. And again, it doesn't matter which one you pick. So let's just go right, and we're going to go up. Now the 28 should be bigger than the 6.2, so just make sure you put those numbers in. 6.82 and 28.2, and then we have our hypotenuse right there. Now the hypotenuse again represents the displacement. So the displacement is going to be, within Pythagorean theorem, 28.2 squared plus 6.82 squared. And that equals to 29.0 meters. We need theta. We talked about the shortcut to finding theta. Theta is going to equal to tan minus 1, opposite, which is 6.82, divided by 28.2. And that equals to 13.6 degrees. Now we need 2 sig digs in our answer. So this is going to come out to 29 meters. We're going to go, in this case, right, because we don't have east and north. So let's just say right, 14 degrees up. And that's our final answer. Now if you had done up and to the right, as in if you had drawn it like this, up and to the right, then you still get the same hypotenuse. It would still be the same answer, but it would be the opposite angle. So instead of up, or excuse me, instead of right 14 degrees up, it would be up 76 degrees right. It's the same answer. To determine the vector sum of the displacement, d1 equals 2.4 meters, 32 degrees south of west, and d2, 1.6 meters south, and d3, 4.9 meters east, 27 degrees south. So what we need to do is we need to draw our vectors. So first we're going south of west. So if we draw it like that, south of west is going to look like that. And that angle comes out to 32 degrees. Then we're going directly south, a little bit less. So that's 1.6. This number here is 2.4. And then we're going east 27 degrees south. So east 27 degrees south, 4.9. Again, that angle right there is 27 degrees. So we have our 3 vectors, we put them head to tail. Now what we need to do is find the vector sum of the displacements. So we're going to break them into our x and y components. So just like we did before, we're going to put our x's in. We'll put our y's in. And we're going to start to solve. So for our y's, it's the opposite first. It's going down. And let's again call right and up positive, just to keep things the same. So for our y, it's the opposite. So it's going to be 2.4 sine 32. And since it's going down, we're going to put a negative sign. We're then going to add that to this negative 1.6 because it's going down. So plus negative 1.6. And then we're going down again for the third one. So we're going to add negative 4.9. It's opposite. So sine 27. And when you put those in your calculator, you get negative 5.096. So let's round that up to negative 5.1 meters. Now for the x, similarly, we're going to go left first. So we're going to say negative 2.4 cos 32. Then it's 0. Then we're going to the right. So we're going to say plus 4.9 cos 27. And when you put that in your calculator, you get 2.33 meters. Now we can draw our triangle. So now we have a positive x, so we're going right, and a negative y, so we're going to go down. So our triangle is going to look something like this. 2.33, 5.1. And then we're going to draw our hypotenuse. We're going to solve for our displacement. Displacement is going to be the square root of 2.33 squared plus 5.1. Again, you don't need to worry about those negative signs. That just tells us the direction that they're going to go. And that equals to 5.61 meters. We need to find theta. Theta equals to tan inverse opposite 5.1 divided by 2.33. That equals to 65.4 degrees. We need 2 sig digs in our answer. So our final answer comes out to, let's draw it up here at the top. Displacement equals to 5.6 meters. Now we're going right and then down. So we say right 65 degrees down. Now if you had done down and then right, it would be down 25 degrees right. Check your understanding. A skater on Ottawa's Rideau Canal travels in a straight line 8.5 times 10 to the 2 meters, 25 degrees north of east, and then 5.6 times 10 to the 2 meters in a straight line, 21 degrees east of north. The entire motion takes 4.2 minutes. So our first vector, we'll draw our compass here. We're going to go 850 meters north of east. So that means we were going east, and we're going to go 25 degrees north of it. So 25 degrees. And that is 850 meters. Then we're going to go 560 meters, 21 degrees east of north. So we were going north, and we're going to go 21 degrees east of it. So it's going to look something like that. 21 degrees. Now we can put in our vectors again. So we're going to go right, and we're going to go up and up. Make sure you draw your vectors correctly, otherwise you'll get the whole problem wrong. And this guy over here, I didn't write it in, is 560 meters. So now we can solve for our x and our y. So this y is a little bit different. Now it's going to be on the adjacent side, on the top one, and the opposite side on the first one. So for the first one, they're both going up, so it's both positive. It's 850. It's opposite, so it's sine 25. It's going up, so it's positive, so plus 560. Now it's the adjacent side, so now it's cos 21. And when you put those in your calculator, you get 882.0 meters. For the x, we're going to have 850 adjacent, so cos 25. Going to the right, so it's positive. Second one's going to the right, so it's positive. 560. It's the opposite now, so it's sine 21. And that equals to 971.0 meters. So now we can draw our triangle. We know we're going right and up, so our triangle, in this case, let's go like this. We go right, and we're going right 971, and we're going up. Oh, let's draw that a little nicer. And we're going up 882, and there's a hypotenuse right there. Again, the hypotenuse represents our displacement. So our displacement in this case is going to equal to the square root of 971 squared plus 882 squared. And that equals to 1,311.8 meters. Now we need theta. I'm just going to do theta over here. Theta is going to equal to inverse tan 882 divided by 971, and that equals to 42 degrees. So now I'm going to write the final answer up here. So what's the skater's displacement? The skater's displacement is 1,311.8 meters. In our drawing, we went east, because that's east, 42 degrees north. Now for proper sig digs, we need two sig digs in our answer. So we're going to say 1.3 times 10 to the 2 meters east 42 degrees north. What are the skater's average speed and average velocity? So to do that, we need to make a little bit of room here. Okay, well, speed is easy. Speed is total distance over time. The distance traveled is 850 plus 560 divided by 4.2 minutes. Right, 4.2 minutes times 60 seconds per minute is going to give us a total time of 252 seconds. So 252 seconds. So that equals to 5.6 meters per second. It's a scalar quantity, so we don't need a direction. And the average velocity is going to equal to our displacement divided by our time. We already found our displacement was 1311.8 divided by the same time, 252. And that gives the displacement, that gives us a velocity of 5.2 meters per second at an angle of east 42 degrees north. And that concludes our lesson on two-dimensional motion.